All right, so sorry I kind of didn't time myself well in that last video and it got cut off, but just to kind of reiterate, in the book they don't run these panics. I mean, they have all the information in there, but they kind of have it in bits and pieces. But I kind of like this setup, and on the test I could even put points to it. A point for this, 1 point for the check, 1 point for the statement, 1 point for the check, 1 point for the statement, 1 point for the check, 1 point for the statement. That's 6 points on the assumptions. Point for the name, point for the formula. Calculate it. Actually, this is just going to be this right here. If you have the formula, you don't really even need to show this. Or if you don't want to put the formula with symbols, you could actually just put this and get credit for the formula. But 1 point for the actual interval being correct. And then usually 2 points for the conclusion. Things you need on the conclusion, context. You need to talk about pennies that are more than 10 years old. The parameter, you need to say proportions. You need to address that it's a parameter, not a sample. So you need to say true or population, and then kind of the other structure. All right? Seems like a lot, but we're going to do it over and over, and you'll be a pro at it by the end. Is it plausible that 60% of all the pennies in the collection are more than 10 years old? Explain. Well, according to my confidence interval, any value in between 43% and 68% is a plausible value. It's unlikely that it would be 70%, for instance. Now, it's not impossible, but it's not likely. It's not plausible. So anything inside here is a likely value. So is it plausible? Yep. Why? Because 60% is in the interval. Okay. Finding the sample size. All right, the margin of error for the one sample Z interval for P is that. Actually, these got to have hats on them. Suppose we want to create a 95% confidence interval to estimate the true population of the true proportion of people in the Woodlands that are Democrat. And we want the margin of error to be 3%. So we want a 3% margin of error. I want 95% confidence. The question you should ask is, how many people should we survey? How many people do I need to survey so that my margin of error is the 3% point that I want? This is what happens before you collect your data in a real study, right? You don't know how many people to survey. You don't want to just go out and start surveying people and get the wrong margin of error, or get an 8% margin of error, or spend a ton of money and end up with a 1% margin of error that you didn't need. So how many people will give us what we want? So we know this, we know that, we want this. Problem is, we don't know this either. So I have two unknowns, and I can't solve it. Too many variables. To handle this problem, we could do two things. There are two strategies for tackling this. We could estimate p-hat using a quick pilot study or using historical data. Pilot study would be, let's just ask 10 people and see what percent are Democrats. If it's 3 of them, then we could use 30% as an estimate. Or look at historical data. 2 years ago, whenever the presidential election happened, 42% of the people that voted were Democrats, so I could use 42%. And then I could put those values in sulfur N. Or we could use the value of p-hat that maximizes this product. This product can actually only take on certain values for sensible values of p-hat. So we could find out what makes this product the maximum and use that. Some nice things about using this method too here, which is what we kind of tend to do more often. We don't have to rely on historical data that may be inaccurate. Suppose I take historical data and it's 0.1. And put that in the formula. That might say I need to survey like 800 people, right? And then I survey 800 people, but my p-hat isn't 0.1. It's something else. And now my margin of error is 4%. So it was wrong. And now I don't have the margin of error I want, and I've already corrected my sample, and I'm kind of in trouble. You don't have to spend time and money on a pilot study. In method 1, if our p-hat was wrong, our sample size may not be enough to get the desired margin of error. I guess that's what I tried to explain right here. So there are flaws with technique 1. If we use method 2, our sample size will always be large enough, and we will always get the margin of error that we want, or one that's smaller. So this is kind of the conservative approach. Now, is there a downside to method 2? Of course. If you use the maximum value, you might predict you need, 1,000 people. And when you calculate your margin of error, you actually get a margin of error of like 2%. In which case it's like, well, gosh, I guess I didn't need to survey 1,000 people. I probably could have got by with 600 or, 900 or something. So sometimes you spend a little bit more money and resources than you needed, but at least you're guaranteed, pros and cons. So let's let p hat equal x, and let's maximize this function. So there's a lot of ways to maximize this function. In class, we went over like 4 of them. But for here, let's just do it real quick. I want to maximize y equals x1 minus x, the maximum product. Expand it out. This is a parabola. Now you should recognize this as a parabola that opens down. Probably looks something like that, maybe. And therefore it has a maximum value. And I want the x value, which is, by the way, the p hat value that maximizes that product. The vertex of that thing is negative b over 2a, if you recall from all your other courses. So negative b is 1 over 2 times a is negative 1. And we can see that basically the p hat that maximizes that is 0.5. Okay? And this is all, you should know that stuff. All of you should know that. But in stats, we don't really care about, the proof of it. You're not responsible, I should say. We do care. So theorem, in order to maximize the product of p hat, q hat, we simply let p hat equal 0.5. So if you want to play it safe, put in 0.5, 50%, and then your sample size is always going to give you what you need, and maybe even give you better than what you need. So let's do this actual example here. Find the sample size required to create a 95% confidence interval to estimate the true population proportion of people in the woodlands that are Democrat within 3%. So, square root of p hat q hat over n times my z crit is equal to my margin of error. So if I want 95%, my z crit is 1.96. If I want to be conservative, I'm going to put in 0.5 for my p and 0.5 for my q. And I want my margin of error to be 3%. Now you could actually say, I want so this is my margin of error. I want it to be equal to 3%, or I want it to be less than 3%. So if you really wanted to get kind of technical with this, we want that inequality there. So this will give me the sample sizes that I need. We could talk about how to solve this by hand. Again, all of you should be able to solve it by hand. But in stats, we're not. It's in an algebra class. So if I'm going to just use a solver. In fact, I'm going to pause it and type it in. All right. So I already typed it in my calculator. I put solve. I put in my inequality, exactly how I had it written, and then you go comma n. This is going to solve for that value of n. I screwed something up. All right, had to pause it because I was like, I don't know what I screwed up. I didn't put in 1.96. Actually, what I put in was, that's how many people you would need to survey if you wanted 99% confidence. Maybe now you know why they don't do 99% confidence. So n has got to be greater than or equal to 1,067.1. N has got to be greater than or equal to 1,067.1. Now, it's tempting perhaps to round to the nearest whole number, but if you round to the nearest whole number, your n is not going to be equal to or greater than that. This is one of those times where you actually always got to round up. So at a minimum, I need this many people. Almost every poll, political poll, news poll is, they survey about 1,000 people because they want 3% margin of error and they're using 95% confidence. So usually those polls are that many people. Now, just to show you, how does your sample size change if you don't use these maximums? Suppose 30% of people in the Woodlands are Democrat. Well, if 30% of the people are Democrat, then you don't need 1,068 people. If we change this to 0.3 and this to 0.7, now you only need 900 people, about. So that's not that big of a difference. It's only a difference of about 160 people, 170 people, but it costs money to survey people, to make phone calls, to do whatever you're going to do. So, but if you predict this and those aren't the percentages, then you might not have enough people. And it really actually changes quite significantly if you start making these even more extreme. If we go 0.1 and 0.9. Now, I know there's more than 10% Democrats in the Woodlands, but just to illustrate to you what happens to the sample size, as you get to the more extreme values, your sample size decreases pretty significantly. So at times, if you have reason to believe that the true proportions are not 50-50 and that it's like left-handed people, percentage of people that are left-handed, well, you know, it's right around, it's less than 20%. So you can survey significantly less people and save yourself money and resources, right? All right, so this is kind of a trivial example. I did not do it in class, and this example actually shows you how to take into account the finite population correction, the one that we learned on that little worksheet. Basically, what happens if the 10% condition fails? Well, this is what happens when the 10% condition fails. It's really easy to handle, but it's beyond the AP Stats curriculum, so you don't need to do it. All right. This is, by the way, this may be the extra credit on the test. All right. Bye.